Have you seen this TikTok trend where people are using magnets to levitate other magnets? It looks like magic, but it's actually science, and today we're going to do it too. Along the way, we're going to talk about quantum mechanics, magnetic fields, and superconductors. Now, if you want to see the full video on this experiment and how we built our own levitating device, check out the channel. So I was scrolling through TikTok one day and I came across this video. A user named Mr. Incredible Physics is doing this demonstration where he can trap another magnet in midair with an invisible force field generated by his large horseshoe magnet. At first I thought maybe there were wires that were holding up the small magnet and it was just really cleverly hidden. But no, he even shows that there are no wires attached. Now at first I thought this might be some kind of ad for a magic trick, but then I started looking at other videos from this same creator and they were all physics related. So I took a closer look at the video. After watching it a few times, I noticed something strange. The small magnet is made of neodymium, which is a type of permanent magnet that has unpaired electrons in its structure. And we know that unpaired electrons have a particular property called spin. They also have an associated magnetic moment. So this means that every single atom in the neodymium magnet acts like a tiny, tiny magnet. All these atomic magnets are aligned in the same direction, so they combine together to make one giant magnet. Neodymium magnets are already really strong. But in this video, he's using a giant horseshoe magnet that is thousands of times larger than the small magnet. So you would think that the small magnet would just get pulled right into the big magnet. But that's not what happens. Instead, the small magnet stays locked in place. Even when he removes the big magnet, it stays locked in place. He can even tap it with a hammer and it doesn't fall down. So how does this work? Is this some kind of new physics phenomenon? Actually, it's just basic physics. This is called quantum locking, also known as magnetic levitation. When a supercooled material enters a magnetic field, it gets trapped inside the field. So it's not like it's floating or anything. It's more like it's locked into place by the magnetic field. If you're wondering what supercooled means, it just means that the material has been cooled below its critical temperature. This critical temperature varies depending on the material, but it's usually around negative 269 degrees Celsius. Now, if you don't have liquid nitrogen on hand, don't worry, you can still do this demo without it. Just let your magnet sit for a while on top of the platform, and then once it's really cold, you can take off the platform. We'll still have a superconductor, but it won't last very long. Now, if you watch the original TikTok, you can actually see that Mr. Incredible Physics used this method, because at one point he takes the platform away and the magnet still remains in place. Now, why does this happen? Why do superconductors behave this way? To answer that question, we need to learn a little bit about magnetic fields. Magnetic fields exert forces on moving charges. For example, if you put a charged particle like an electron into a magnetic field, the magnetic field will exert a force on the electron that is perpendicular to both the velocity of the electron and the magnetic field lines. This force is what causes the electron to move in a circle. This is actually how cathode ray tubes work. By changing the direction of the magnetic field lines, you can change the path of the electrons and where they end up hitting on the screen. But magnetic fields also exert forces on other magnetic fields. When you put two magnets next to each other, you probably already know that they will attract or repel each other. This happens because the magnetic field lines from one magnet flow into the other magnet. And when they come out of the other side, they form a closed loop. It's like the magnetic field lines are trying to get back to where they came from. So when the field lines come out of the north pole of one magnet and flow into the south pole of another magnet, the force is attractive. But if the field lines come out of the north pole of one magnet and flow out of the north pole of another magnet, then the force is repulsive. When you put a superconductor into a magnetic field, something interesting happens. The magnetic field lines can't penetrate the superconductor. They get pushed out. This happens because the magnetic field lines push on the electrons in the material. And since the electrons are free to move in a superconductor, they rearrange themselves to form a current. This current generates its own magnetic field. That magnetic field opposes the external magnetic field. Eventually, the opposing magnetic field is strong enough to completely push the external magnetic field lines out of the superconductor. In fact, it turns out that the electrons in the superconductor can rearrange themselves to generate an exact opposite magnetic field. This is called perfect diamagnetism. So when you put a superconductor into a magnetic field, It perfectly cancels out the magnetic field inside the superconductor. This is why it's called a magnetic shield. Now, what happens if you put a magnet inside a magnetic shield? Since the magnetic field lines can't penetrate the shield, they get pushed up against the shield until they form a wall. This is called magnetic pressure. Magnetic pressure is real. It's not just something that happens in cartoons. In fact, it's what keeps our sun from collapsing in on itself. The magnetic pressure from the sun's magnetic field prevents the sun's gravity from pulling everything together. So now if you take a magnet and push it through a magnetic shield, the magnetic pressure from the field lines will push back on the magnet. It's like there's an invisible wall that's stopping the magnet from going any further. This is what happens when you try to put a magnet through a piece of lead. The magnetic pressure from the field lines pushes the magnet back out of the lead. You can actually see this effect pretty clearly in the video. Notice how the small magnet doesn't go all the way through the platform. It stops about halfway through. The reason why is because the platform acts like a magnetic shield. The electrons in the platform can rearrange themselves to form a current that generates a magnetic field that opposes the external magnetic field. This means that the magnetic pressure from the field lines of the big magnet is pushing back on the small magnet. The stronger the magnetic field, the stronger the magnetic pressure. This is why the small magnet needs to be supercooled. It's not supercooled, it's not the magnetic field from the platform will be too strong and the small magnet won't be able to pass through. But if the platform is supercooled, then the magnetic field from the platform is much weaker, and the small magnet can pass through the platform. Once the small magnet passes through the platform, the magnetic pressure from the field lines of the big magnet is strong enough to hold up the small magnet. It's like there's an invisible force field that's holding up the small magnet. This is called quantum locking, or magnetic levitation. It's the same principle that is used in maglev trains. In a maglev train, the track generates a magnetic field that repels the magnets in the train. This repulsion is what makes the train float above the track. Now, if you think this is cool, wait until you see what happens when we put two superconductors next to each other. We'll talk about that in the next video. Alright, so now it's time for the riddle. I float not because of wind or wires, but because of quantum rules. What am I if you thought about magnetic levitation or superconductors? You'd be correct. Hover over the subscribe button, and I'll see you in the next video.